Okay, so problem 18, problem 1826 in the book. All right, so problem 1826, it says at 25 degrees Celsius, the molar solubility of silver phosphate, AgPO4. Now the phosphate has a +3 charge, so there's 3 silvers on silver phosphate. The molar solubility of silver phosphate is 1.8 times 10 to the minus 5. So that means KSP equals 1.8 times 10 to the minus 5. Now KSP is an equilibrium K for the solubility product of this thing. So we're assuming that there's a degree in which silver phosphate, although it's generally insoluble, does dissociate to a small degree, and this is the value that represents it. The separation is 3 AGs, right, for every one PO4 3 minus. All right, so that is the association expression, and the KSP would be the K for this equation here. The solid isn't going to be involved, obviously, because it's a solid, so then we can say that KSP would be equal to the concentration of the silver ion cubed and the concentration of phosphate, PO4 3 minus. So this is the silver ion, PO4 3 minus. All right, so if KSP doesn't equal this, this is the molar solubility. Molar solubility. So that is how many moles of this will actually dissolve. So that tells us how many, the molar concentration of the phosphate ion. The molar concentration of this will be 3 times as much, and it'll be in here. So what I need to do is I need to recognize that this is how much of this stuff is going to dissolve, the molar concentration that will be dissolved once you put it in solution. That means the phosphate concentration will be equal to that, 1.8 times 10 to the minus 5. The silver ion concentration won't be equal to that. It'll be 3 times that. So if we put 1.8 times 10 to the minus 5 times 3, 5.4 times 10 to the minus 5, but we're also going to need to cube that. So we raise that to the value of 3, cube it, and then we multiply this times 1.8 times 10 to the minus 5, and that gives us a KSP value of 2.8 times 10 to the minus 18, and that should be the KSP that we're looking for, 1826. .8 times 10 to the minus 18. All right, so that's 1826, 1828. Which compound is more soluble in water, zinc carbonate or magnesium carbonate? Zinc carbonate or magnesium carbonate? Now, let's see, CO3 2 minus, zinc is a +2, yeah, so those are the compounds. We have to know their KSPs, right, to calculate solubility. We need to know what their KSP, which one is more soluble. So if there was a table in here that would tell us the solubility products of these, all right, then we could see. And the one that was more soluble would have the larger solubility product. All right, so let's see, the carbonates, is that here somewhere? Here we are on page 832. We have the zinc carbonate, 1.5 times 10 to the minus 10. And magnesium carbonate, 6.8 times 10 to the minus 8. So the higher number is going to tell us that more of it is on the right side of the equilibrium expression for the solubility of the compound that we're interested in. So it has to be this one. So magnesium carbonate has to be more soluble. All right. 1828 magnesium carbonate. Yep. All right. So again, that table is on page 832. 1830. All right. What is the molar solubility of lead bromide in water? So here we have PbBr2, and we want to know how much of it dissolves. Well, we can go back to our table and find out the KSP. On page 832, the KSP for lead bromide. Is it there? There it is, 6.6 times 10 to the minus 6. 6.6 times 10 to the minus 6. That is how much, or that's not the molar, it's not the molar solubility, right? It's just the KSP. So the KSP for lead bromide would be, we can imagine 1 lead ion and 2 bromide ions, right? And so it would be the concentration of the lead ion times the concentration of the bromide ion squared, right? So this again is not included, it's a solid. So this value, KSP, equals 6.6 times 10 to the minus 6. That equals, now the concentration of the lead ion is going to be, we can put that as X, and the concentration of the bromide ion is going to be twice as much, that'll be 2X. And so we can solve for X there, and that'll tell us how much lead ion is the molar concentration of the lead ion, and that'll also be equal to the molar solubility. All right, so we have this value equaling 2x squared, or 4x squared. 2x squared is 4x squared. So we take this and square it. So x times 4x squared equals 4x cubed. So we take our molar solubility, divide by 4, and then take the cube root. All right, so we have 6.6 times 10 to the minus 6. Divide by 4. And then we take the cube root. I take the cube root by raising it to the 1 over 3 power. All right, so I'm getting 0.118 molar. Let's see if that's right. 1830. Yep, that's it. All right. So, 1832. Calculate the molar solubility of zinc cyanide in water. Ignore the reaction of cyanide ion with water. Okay, so if we have ZnCN2, right? We need to know the molar solubility of this. So we have, not on the same table though, right? Where is the cyanide ions, right? Where are the cyanide ions? Solubility. Which page is cyanide ion? Well, maybe there's a chart in the back of the book, but let's see if I can find it on the internet here. Molar solubility of zinc cyanide. Molar solubility of zinc cyanide. Is there a table at the back of the book here? Solubility product constants. Fluorides, bromides, iodides, hydroxides, cyanides. There it is. Alright, so on Appendix C, 845, we have the KSP for the zinc cyanide, which is 3 times 10 to the minus 16. 3 times 10 to the minus 16. So, then, we will that's the KSP for zinc cyanide. And again, in 832, what are they asking for? Technical molar solubility. So, there's 2 cyanides that dissociate. And 1 zinc ion for every zinc cyanide formula unit. So the equilibrium expression is cyanide ion squared times the concentration of the zinc ion. Alright, so the concentration of the zinc ion is going to be twice as much as the concentration of, the concentration of the cyanide ion is going to be twice as much as the concentration of the zinc ion. So that will equal 3 times 10 to the minus 16. Now, this is 4x squared times x, so that's again 4x cubed, and that's going to be equal to 3 times 10 to the minus 16. So 3 times 10 to the minus 16 divided by 4, and then we're going to take the cube root of that, and that's 4.2 times 10 to the minus 6. And that should be the molar solubility, because that's how many moles of zinc there are, and for every 1 mole of zinc, that's 1 mole of zinc cyanide that will ionize. 1832, 4.2 times 10 to the minus 6. All right. 1834, 25 degrees Celsius. Lithium, what is it? Lithium fluoride. KSP, 1.8 times 10 to the minus 3, and for barium fluoride, 1.7 times 10 to the minus 6. Which salt, lithium or barium, has the larger molar solubility in water? Calculate the solubility of each in units of moles per liter. Alright, so you would be tempted here to just say, oh, the barium or lithium fluoride is a higher number, and so it would have a higher molar solubility, but you want to be sure that you're not being confused by the fact that in one expression you're going to have more, so KSP is not obviously just molar solubility, it's the concentration of the components. But in this thing, I think in this situation, I think you're going to be right anyways. But we'll take a look here. Lithium fluoride is dissociated into lithium ion and the fluoride ion, and this equilibrium is 1.8 times 10 to the minus 3. That equals the concentration of lithium times the concentration of the fluoride ion. Right? Whereas the other one is 1.7 times 10 to the minus 6. Barium fluoride. So we have barium plus 2 ion, and we have, well, it's just ionizing the barium ion and then 2 fluoride ions. And so the equilibrium expression is going to be 2F, or no, F minus squared, oops, yeah, F minus squared there. And this is barium plus 2 in its concentration. All right, so this value here is going to be 1834 1.7 times 10 to the minus 6. So the square root of this value here, because if I put x into both of those, that will be x squared. So the square root of this value will be the molar solubility of the lithium fluoride. For this one, it's going to equal, again, the concentration of fluoride in here is going to be 2 fluorides, right? 2s. So it's going to be, again, the 4x cubed. All right? So we have to solve for x for each of these. 1.8 times 10 to the minus 3. Take the square root of that. This molar solubility is 0.424. This one here, 1.7 times 10 to the minus 6, divided by 4, and then take the square or the cube root of that, 0.0075. All right. So then that would suggest that the barium the lithium fluoride is more 34 is more soluble, which is right. Okay. 1836. All right. A salt whose formula is Mx has a KSP of 3.2 times 10 to the minus 2. Another sparingly soluble salt, Mx3, must have what value of KSP if the molar solubility of the two salts are to be identical? All right, so if they have the same molar solubility, then Mx dissociates into M plus X minus. Mx3 dissociates into M plus 3 plus X3X minus. The KSP for this top one, KSPMX, has to be equal to concentration of M plus times the concentration of X minus. Whereas the KSP for MX3 has to be the concentration of M plus 3 times the concentration of X minus cubed. All right. If I put an X in for these, let's see, what does it say? Let's see, what must the value of KSP be? Oh, so we know that the KSP for this one is 3.2 times 10 to the minus 10. And we want to say if they have the same molar solubilities, then what will the KSP of this one? Well, the square root of this value will be the molar solubility of this one. And then if we put that one in here, the molar solubility of this one, where do we find it? This is again going to be the 4x cubed. So we take the molar solubility, cube it, multiplied by 4. That would tell us what the KSP for this one would have to be. So if we take the square root of this one to find the, because if we call these x, the concentration of this is equal to the concentration of that, so x squared. So 3.2 times 10 to the minus 10. And we take the square root of that value. All right, so x then is going to be equal to, for this one here, x equals 1.79 times 10 to the minus, well, 5. 10 to the minus 5. All right, so now that's the molar solubility. If this is going to have the same molar solubility, we can take that value, we can cube it, we can multiply it by 4, and that gives us a KSP value of 2.3 times 10 to the minus 14. So, what must the KSP value for MX3? So yeah, that's what we're looking for. So 1836, 2.8 times 10 to the minus 18. 2.8. That's 1836. A salt is formula MX of the case be equal to 3.2 times 10 to the minus 10. 3.2 times 10 to the minus 10. Did I do that right? 3.2 times 10 to the minus 10 to the square root of it to find out what the molar solubility of this is. We got that. The molar solubility of this was 1.79 times 10 to the minus 5. Take that value, put it in here if it has the same molar solubility. That value. Oh, no. This concentration here is going to be 3 times 3x minus, right? So this value that goes into here, well, let's multiply it 3 times. So the value is 1.79 times 10 to the minus 5. We're going to multiply it by 3, and then we'll cube it, and then we'll multiply it by this value again. 1.79 times 10 to the minus 5. Alright, so that gives us 2.7 or 2.8 times 10 to the minus 8. 1836. 2.8 times to the minus 8. Okay, good deal. 1838. Calculate sulfate. Calcium sulfate is found in plaster at KSP of 4.9 times 10 to the minus 5. Sulfate. 4.9 times 10 to the minus 5 is the KSP for that. Alright. What is the calculated molar solubility of K potassium sulfate in water? Calcium sulfate is found in plaster. KSP is that. So, this is how it's going to dissociate. The concentration of the calcium can be identified as X, the concentration of the sulfate also. So that is going to equal 4.9 times 10 to the minus 5. And we can just take the square root of 4.9 times 10 to the minus 5. Okay, 0.007. Oh, this was 1838. Yep. All right. 1840. It was found that the molar solubility of barium sulfite in 0.1 molar barium chloride is 8 times 10 to the minus 6. What's the value of KSP? Okay. So, barium sulfite, it dissociates like this. So the KSP is going to be equal to the concentration of this times the concentration of that. But we have some barium chloride already in solution. So how does that affect things? Well, we can think of, kind of use somewhat like an ice table. Let's put this KSP down here a little bit. And say the initial concentration of the barium in solution now, because we had barium chloride, was 0.1 molar, 0.1 molar. And the amount of sulfite here was 0. But as soon as, so this is our initial concentration change, we have to go to the right. So we're going to increase some, but it's not going to increase as much because there's some of this barium pushing back the other way. So the equilibrium concentration then is going to be 0.1 plus X, and this is going to be X there. So now the KSP will be defined as the concentration of the barium times the concentration of the sulfite. So it's 0.1 plus X times X, and that will be the KSP. So that's X squared plus 0.1x equals the KSP. We are given the KSPs, I don't know, 1840. We're given the molar solubility, 8 times 10 to the 6, 8 to the 10 to the minus 6. So the molar solubility is 8 times 10 to the minus 6. That's how much barium sulfite actually dissolved, right? So 8 times 10 to the minus 6 is going to be the value of the sulfide ion, the value of the X, right? So if I put 8 times 10 to the minus 6 squared plus 0.1 times 8 times 10 to the minus 6, that should tell us what our KSP is. Alright, so 8 times 10 to the minus 6 squared plus 0.1 times 8 times 10 to the minus 6. So I'm getting 8 times 10 to the minus 7. 1840. 8 times 10 to the minus 7. Okay. Good. 1842. Copper 1 chloride has a KSP of 1.7 times 10 to the minus 7. Copper 1 means the copper ion has a plus 1 charge. And the chloride ion has a plus 1 charge. So KSP 1.7 times 10 to the minus 7. Calculate the molar solubility of the copper chloride in pure water first. So it's going to be the copper concentration times the chloride ion concentration. That's going to be equal to 1.7 times 10 to the minus 7. That's in pure water. 1.7 times 10 to the minus 7. Take the square root of that value. Get 4.12 times 10 to the minus 4. That's the molar solubility of the stuff. So that's 1442. We want to find the molar solubility of that. Yeah, now we need to find the molar solubility in 0.2 molar HCl, and then, or 0.02 molar HCl, and 0.2 molar HCl, and then 0.15 molar calcium chloride. Okay, which is 0.3 molar chloride. So the first two scenarios give us a chloride ion, which is a common ion, right? It's an ion that's common, so it's going to push the equilibrium to the left, and less of it is going to dissolve. So we have first part B, number B, which is the second scenario. 0.02 molar HCl, so 0.02 molar chloride ion. Let's check this one really quick before we erase it. 1842A. 4.1 times 10 minus 4. Alright, so now we can erase this. And go to part B. 2.02.